Then I would suggest we continue with the next very interesting subject. It's integration and control of agent models. And our speakers will demonstrate the integration of the IK driver model into the simulation tool OpenPass with help of the standards FMU and OC. And Daniel Becker, who's a research associate from University Aachen, Institute for Automotive Engineering, is involved in model development of traffic agents and static environment. Our second speaker is Thomas Bleher. He's a software developer working for BMW in software developing, and he is dealing with the pedestrian model and is involved in extending and improving the standard interfaces for pedestrian and real-time simulation. And as a third speaker, we have Heinz Sachsenweger. He's team lead of environmental and vehicle simulation in ZF Friedrichshafen AG, and he will give us information about the abstract behavior of traffic agents. Then let's start with Daniel. You already can see the presentation. Stage is yours.
Thank you very much. I would like to welcome you also to this session about traffic agents in the context of Z-level. As introduced, I'm Daniel and I will sharing this presentation with Thomas and Heinz. The session is structured as shown on the slide. I will give a brief introduction to OSMP, the OSI sensor model packaging, then introduce how we integrated our IKA driver model. Thomas will show how the integration of a pedestrian model works, and Heinz will conclude the session with abstract behavior of traffic agents. The OSI sensor model packaging framework, short OSMP, originates from sensor modeling development, as the name indicates as well. The goal is to have a framework that makes it easy to generate a functional mockup unit, FMU, that takes OSI as an interface. When starting the work in Z-level, we adapted the work already done in the GitHub OSI repository and forked it into the Z-level GitLab. We then conceptualized required changes in the specification of OSMP and implemented an example that works with OSI messages appropriate for agent models. In milestone 1 of the Z-level project last year, a first proof of concept was shown. As a result, the extensions in the OSMP specification were contributed to ASAM OSI, a standardization project, and are currently publicly available. As I understand, a possible renaming towards a more general name is under consideration within the ASAM OSI project. Now let us have a closer look on the OSI messages which are exchanged between the simulation environment and the traffic agent. You see on the left-hand side the environment simulation, in this case OpenPass, for example. On the right-hand side, the traffic agent FMU is shown. The interface messages are divided into 2 stages. First, there is initialization where the traffic agent receives a ground truth init message, which can be used for static information that doesn't change during the simulation. In addition, the agent requests its sensor view configuration, so the field of view and what should be contained in the sensor view, and receives a confirmation of that. The messages that distinguish a traffic agent from a sensor are printed in bold. The other stage is during runtime. 3 messages occur here. The sensor view, as configured in the initialization phase, holds all relevant information about the environment, which is specified in the sensor view config, as I said. In each time step, the simulation environment can send a so-called traffic command to the traffic agent. That might be trajectories or a position that shall be acquired, or lane change command, and so on. The commands here are aligned to open scenario. Finally, the traffic agent provides its new state called traffic update as an output. Now that the OSMP framework is briefly introduced, let's have a look at an example how that might be used in traffic simulation. The FMU, which is included by the simulation software, is indicated by the light blue box. Besides the actual driver behavior model, it consists of an adapter that translates the OSI messages into an internal interface. After the model calculates desired acceleration and curvature, a very simple vehicle model translates those into updated vehicle states. The user interfaces have been introduced earlier and are shown here again. Another OSI message that is not yet specified in OSMP, but only conceptuated right now in set level, is the dynamics request, which would allow to replace the internal simple vehicle model by an external FMU that calculates the traffic update then. Let us have a closer look on the two modules we at the AKA worked on in set level, namely the OSI adapter and the agent model. The OSI adapter interprets the OSI ground truth and transforms all relevant signals into the internal interface of the agent model. The basis for the driving path is the OSI center line here. In addition, all traffic commands are parsed and provided in a given format to the agent model. The AKA driver is a behavior model that is structured aligned to the descriptive models of Rasmussen and Donges, if you know eventually those models. That is reflected by the stages decision, conscious, and subconscious. In those stages, various modules are implemented. This can be illustrated by the example of stopping. First, the decision has to be done to stop at that a stop is required. That could be a stop sign or after the analysis of surrounding traffic at a yield sign. Then, in each time step, the conscious value distance to stop is calculated and then is controlled in the subconscious model for stopping with an acceleration. We implemented a set of basic maneuvers to be able to perform simple driving tasks. On the next slide, I will give an overview on the current capabilities of the model. The capabilities can be illustrated as a state diagram and are divided into longitudinal and lateral operations. The boxes you see represent stable driving states where one conscious value is controlled to be constant. This could be a velocity or a time headway, for example. The solid arrows are modeled capabilities as well. For example, if a speed limit comes up, the smooth adjustment of velocity is modeled explicitly. Dashed lines are transitions that happen implicitly. For example, if the driver follows a vehicle that then stops. Let's take the example of a driver that drives at its comfort speed to illustrate the concept again. We are located in the keeping speed state then. Then a speed limit appears and the capability change speed is executed, where the speed is reduced and reached at the point of the speed limit. After that, the control variable speed is maintained again. A similar process is carried out when approaching a leading vehicle. The conscious variable there is then not a speed anymore, but a time headway. If the leading vehicle stops, the example I mentioned earlier occurs that we implicitly end up in standing, where the conscious variable is speed equals 0. To show the result of the work we have done in the first half of the project, I would like to show a video. We see a junction that is populated by various traffic agents. All of them are controlled by the AKA driver and react on each other in this closed loop simulation, which is similar to the simulation use case 1 example and is simulated at OpenPath as well. The upper left and lower right junction arms are priority roads, so that agent 3 and 1 has to yield. So let's have a look. So we see agent 1 and 3 wait until the junction is clear and then carefully pass the junction. We see there are no crashes so far, and we see that obviously we drive with a comfortable curve speed because in the curve we are slower than when driving on a straight line. So this simulation shows the capabilities, almost all capabilities of the driver model so far. And with that, I would like to hand over to Thomas, who will tell you more details on pedestrian models in our simulation framework.
Thank you, Daniel. Yes, so as part of the set-level project, I've been working on integrating a pedestrian model. And on the first slide, I want to show what are we aiming for. So we want to simulate human behavior and vehicle interaction for different types of simulation using standard interfaces. Yeah, why is I think a good question. Why go to the trouble of implementing a pedestrian model instead of scripting everything? And my answer is that human-in-the-loop simulation is an important part of testing the autonomous driving function. And for human-in-the-loop simulation, it's necessary to have agents that interact with other agents in the environment and also interact with the ego vehicle. And especially for urban scenarios, you need pedestrians to create a believable scene. So that's why we want to have agents that can challenge the autonomous driving function, that can interact with the driver. And since it's some work to develop such a model, we would like to use that for different types of simulation and therefore use standard interfaces. In this case, ASM-OSI and the FMI standard. And in the next slide, I will show you the current state of the model. So we spend a lot of work on getting the messages right. As Daniel already told, we created some new messages, these OSMP ground truth init and the traffic command and traffic update to make sure that we can probably handle these models. On the functional side, you can see that we have a model now that uses pathfinding via theta star, so it can find its own path along the map. It can avoid other pedestrians via the social force model, and it can react to other vehicles. The model is available under an open source license. It is packaged as an FMU shared library, and we invested a lot of effort to make sure that it can be handled efficiently. And the reason is that if you have a large simulation, you might have a lot of pedestrians, and so it's necessary for the calculation and to be efficient. Think of something like calculating where on the map the pedestrian can walk on. So that's the current state. And now I would like to show some of the challenges that we've been facing. Yes. Some of them solved, some of them yet to be solved. The first challenge I want to mention is representing the walkable space. So OpenDrive, but also other maps used for autonomous driving simulation represent a road very well, but the space of the pedestrian not so well. For example, okay, where beside the road can a pedestrian walk? There's some ongoing work on that. Hopefully OpenDrive 2.0 will include some functionality. There's some talk of integrating better with CityKML, for example. The next task was efficiently handling a map for real-time simulation. We did some work on that. So we have this ground truth init message, which means that the map is transmitted before the simulation starts to the pedestrian, and some expensive calculation can be done offline. But I think there are further improvements that are needed, for example, using flat buffer instead of protobuf to reduce the number of memory allocations. There's ongoing work in that area. Then we have the topic of representation of junctions. Currently, junctions in ASM-OSI are not represented very well. There are no lanes on the junction. There is no drivable area, and there's ongoing work, probably OSI 4.0. Then OSI 3.2 didn't contain any sidewalks, which made it basically impossible to implement pedestrians using OSI. This was solved in OSI 3.3. That's nice. And we're also working on pedestrian movement. Things like, okay, this pedestrian is currently looking at its mobile phone. It's looking left and right before crossing the street. How it moves, things like that. That should also be represented in the environment description, and this is also being worked on for OSI. So after we have looked at the challenges, I would like to show you a short demo video of the current state. This is on a small test simulator, and you can see some pedestrians on the side, in the right side now, and here also on the left side. These all the pedestrians that are moving are animated using the OSI pedestrian model, connected via an FMU and OSI to the simulator. Yes, and so they already can find their path by themselves. For example, now on the right side of the street, you can see another pedestrian. And now we come to a crosswalk. And here you can see some of the use cases which can be used. This is manual driving, but if you drive autonomously, it would be interesting to see, does the autonomous driving function detect which pedestrians walk across the street and which do not? Yes, so that's the current state. As you can see, there's no animation yet, so that's the next step we want to tackle to make it really useful for human-in-the-loop simulation. And with that, I hand over to Heinz Sachsenweger, who will continue with the abstract behavior of traffic agents. Thank you.
Thank you, Thomas. Then, as Thomas just said, the topic now is abstract behavior of traffic agents. What are we trying to do here? We are trying to simply see how we can transfer intelligence from the scenario engine in our models using known, let's say, standards like Open Scenario and OSI. This will cause for decentralization of intelligence behavior. So how does our setup look like? Daniel, could you please move to? Yes, thank you. So for this purpose, we have chosen Open Scenario version 1.0 and Open Drive 1.6, which is standard in ASAM. Standard. Then using our custom command, because this is still not standardized, we send those files to OpenPass. There we added some modification to the tool OpenPass. And after that, the OpenPass in there they have scenario engine. We send OSI custom message to our models. In this case, it will be the pedestrian agent. Here, since we still haven't standardized those messages, we are using custom commands. The custom command we will show in the next slide in a bit more detailed. So we can see here once again our Open Scenario engine in OpenPass and our agent. In this case, the agent is our pedestrian. And now let's look a bit more in details how our custom commands look like. So in the Open Scenario, we have the following text. So it's ignore all traffic participant. So you can say, so this is a simple example simply to show how it could look like. So once we see how it look and we can evaluate it and then modify it and then also go and standardize it. So the Open Scenario send simply ignore all traffic participant using the custom command action to the scenario engine. The scenario engine interpreted it and sent an OSI message using the custom action. This is the format above, and below we can see exactly the command which we sent using OSI in a string to our agent. Now we would like to see the videos. So the setup which we chose, we have the agent, the pedestrian number 0, which is going to cross from the upper side to the lower side in a then we go to the agent 1. The agent 1 is also a pedestrian, which is simply going to go from down up. In addition, we have our driver model, the agent number 2, which is simply going to drive from the left side to the right, and parallel we have the driver model agent number 3, which is going to drive from the right side to the left side. The aim here is to see some kind of symmetry, and later we will send the agent number 0 the command ignore all traffic participant with the value true. But in this case, in this folio, we are going to see first if we don't send this command. So that's it going to look like. So the pedestrian are waiting until the cars are going away, driving away, and then they are crossing safely the road. And the way of, now we are going to the second folio where we send the ignore all traffic participant a command to the agent number 1. The interpretation of this command is already implemented in the model, in the pedestrian model, and we simply want that our agent behave or have the implementation inside them. So it's mean I don't need to modify my open scenario file. So the intelligence is already in the driver, or in this case in the pedestrian. So let's see how it looks if we send this command. So the agent 0 simply ignore the vehicles which are driving before him and simply cross the road. From the other side, the agent number 1 is waiting. So, oops, that was too fast. So what we can see here, this is a very nice example. The two vehicles slow down as they see the person, the pedestrian number 0, crossing over. So in the scenario, both of the cars started from 50 km/h, and we can see here that the agent number 2 have a velocity of 2 km/h. It's almost stopping due to the pedestrian, and the agent number 3 reduced his speed from 50 to 34 km/h. And so we see here that the way that using those custom commands, we were able to give a new intelligence which was before that not there to the so what have we seen until now? We were able to show that the intelligent driver and pedestrian model using the Open Scenario 1.0, those modules which develop as part of Z-Level founded project are going to be available as open source at the end of the project, at least at the end of the project. And our next task from what we show here will be to standardize those messages that at the moment as custom command, and that we are going to take place in the next half a year of the project. So I hope you enjoyed the presentation, and I would like to thank also Daniel Becker and Thomas Bleher for their side on this presentation, and I'm giving back the talk to you.
Thank you very much. Thank you, all of you. That was very fascinating for me, I must say. And we have a few minutes left, exactly 6 minutes. So Daniel and Thomas are available for questions. Julian, if you want to point in a question, do we have some?
Yes, we got a lot of questions. And the first question goes to Daniel. Regarding your driver model, the question is when will this driver model be open sourced available? Can you say something on that?
Well, that depends what's the whole model. The behavior model is the core is available on GitHub already, but the adapters to use it with FMI and OSI are still under work, let's say, and we did that within set level, and we are trying to bring them to a state where we can publish them, but at least at the end of set level, I mean, that should be the goal of set level. They probably will be available so that we can integrate the model with open standards, but the, let's say, the core of the behavior model at a given state of work is available right now on GitHub on our AKA page, but probably not ready to integrate.
Okay, thanks. So we have a further question. This goes to Heinz. So how do you send the custom comments to your agents? Do you use OSI protobuf or flat buffer, or do you send it as a string directly? So maybe can you remind us how you did this?
This is a good question, Julian. We are using the protobuf technology, and there in the folio, in the slides, which was shown before, then it's really a string which we are sending to our agent, in this case, the pedestrian. So this is like a simple, this is not optimized way, it's simply a way to test the functionality. It will be improved in the further second half of the project. And I hope I was able to answer your question.
Okay, do we have time for last question, Stephanie?
We do have 4 minutes left, so if you have one other question, go ahead.
Yes, so this would be going in direction of, okay, if I have an agent model, I can have the intelligence inside the model, or I can use the command I give to this model to bring him in a specific situation. So where do you see the need to have a specific intelligence inside the model itself? Maybe this question goes to Thomas.
Okay, we'll try to answer that one. I think so. There are some places, and one which I am familiar with is if you do human in the loop simulation. So you put an actual human in a simulator and try to create a scenario, and there you need interaction. So you, depending on how fast, for example, you drive towards pedestrian crossing, pedestrians should react differently. I think it also helps with creation of scenarios. So if you have very dumb models, then you need to put a lot into the scenario description. And for example, if you have a model that can do its own pathfinding, and you just give it a start point and an end point, and it will find its path along the sidewalk itself, this makes it much simpler to create a scenario.
Thank you, Thomas. Do you have another question for us, Julian?
Yes, I would have a last question. So in the example you shown, are the sidewalks and possible pedestrian paths model with OpenDrive? Or how did you do it? Who wants to take this question?
I can take this question. So yes, this is an OpenDrive map, and the sidewalks are modeled as OpenDrive lanes of type sidewalk. And the zebra crossing you saw, it was modeled as a signal, and I think there's also an OpenDrive object there.
Wonderful. Thank you very much. I hope that answered all our questions. And thanks all of you for the very interesting contributions.